This is going to be a video going over some of the basic handling characteristics and also some of the basic tire characteristics that you're going to encounter in FSAE design. We're going to start here by looking at the characteristics of our tire and wheel. Now you'll see the wheel itself is comprised of two key components. First you have the metal rim on the inside and then the rubber tire on the outside. The tire is our primary source of concern, and this is the most important part of your vehicle system in terms of handling. Every force that you generate in your suspension system and your drivetrain system has to make its way through the tire at some point in order to gain purchase with the ground and actually generate a force to move your vehicle. The design and choice of your tire dynamics is one of the most important parts in putting together your vehicle, and so it's very crucial that you pay attention to the properties that the tire generates. Some key things to note here. One key component is that this tire itself is not a completely rigid object. This tire acts as a sort of spring. It has a spring coefficient to the rubber. The rubber can compress. The amount that it does is dependent on how much air pressure you put inside the tire. A tire that's inflated more is going to compress less. A tire with lower air pressure will compress more. But it's important to understand that the tire itself can compress and does not stay perfectly round. Rather, at the bottom of the tire where you have the most compression, you will have a flat contact patch. The contact patch is what will actually come into contact with the ground. It is not a single point on the tire, but rather a splayed out surface of the tire itself after it's been compressed. The size of your contact patch is going to be dependent of the flexibility of the rubber in the tire, the amount of air pressure you put in, and also how much load is being applied to the tire itself. And something that is key to understand here is that the contact patch itself, in relation to the ground, we can consider as a static object. It's not moving relative to the ground. Despite the fact that the tire is constantly rotating, whichever point you have in contact with the ground itself can be considered a static object as long as the tire is not slipping. As long as you have traction between the tire and the ground, this point can be treated stationary. This is a bit easier to understand if you watch a video of a tank where the tracks are laid on the ground. You can see that the track itself, the point at which the track contacts the ground, is stationary until it comes and gets picked up around the back edge. The same thing is happening here with your tire, the difference being you have a small flat portion on the bottom of your tire rather than a spot on the track of a tank. But it is important to understand that we can treat this bottom patch as if it was in contact with the ground and stationary, despite the fact that the tire itself is rotating. It's only for an instantaneous moment, but for that moment you can analyze it as if it was a static object. And in this object, you're going to be generating friction between the tire and the ground independently in a longitudinal and lateral direction. The properties of the tire are such that you are not going to see the same friction longitudinally and laterally across a tire. It will be different, and you have to treat them as though they are different properties themselves. There are a lot of models that you can use in order to model the forces generated by a tire. We won't be going into that today because it's just far too complex of a subject to get into. But you must understand that the longitudinal and lateral forces are not the same and will be generated independently of each other. It is a bit clearer to see if we look at what we refer to as the friction ellipse down here. On this ellipse, this is considering your maximum lateral and longitudinal force on the tire. We will treat the lateral force as in the Z direction and the longitudinal force as in the X direction. Generally speaking, you will see that you're capable of generating more lateral force on the tire than you are longitudinal. As such, you'll generate more acceleration in a turning motion, so a lateral acceleration rather than longitudinal acceleration. And the friction between the two of these, the friction coefficient, is not the same. As such, we don't get a perfect circle all the way around. You get a bit of an ellipse, where the maximum force you can generate in the longitudinal direction is going to be lower than the maximum force you can generate in the lateral direction. Along this ellipse, at any point, this is referred to as the maximum amount of force the tire can generate in any direction. So let's say we have at a 45-degree angle here onto our ellipse. This is a point where you're generating half longitudinal, half lateral acceleration. So let's say this is you braking into a corner. The most force you can possibly generate is going to be the point along this friction ellipse. That's under ideal conditions where your coefficient of friction holds true. In reality, this is not a perfectly accurate representation, but this is about the best estimation you can make on sort of a quick reference sheet. And there are a few factors that are going to affect the grip of the tire itself. One of the most important ones is the tire temperature. A cold tire will not generate its optimal friction, But likewise, a very hot tire is not going to generate the optimal friction either. There's a sweet spot in between the two of those that the tire is designed to operate at, and you want to set up and test your vehicle in a way that you maintain this optimal temperature for as much of your run as possible. Adverse conditions will sometimes put you under or over the maximum temperature that you can allow. However, you should shoot to always go for the optimal tire temperature. This is going to be different for every tire. It needs to be tested empirically to find out, but it is important to monitor and keep an eye on. Also affecting your tire grip is the contact patch size. Now, this is a bit counterintuitive in the sense that a larger contact patch will generate more lateral friction, or lateral force, but the coefficient of friction itself is not changing. The coefficient of friction is a constant regardless of the size of the contact patch. The coefficient of friction of a tire is dependent on a few other properties, such as the camber angle or the toe angle of the tire. However, it's independent of the size of the contact patch itself. The reason that a larger contact patch is going to generate more force for you is that you have increased surface area in contact with the road and a higher probability of having good purchase between the rubber and irregularities on the road surface. We're not working with two perfectly smooth objects, and as such, you're going to notice that there are gaps in between the tire and the road. You're only getting contact in a few areas along the contact patch itself. So the larger of an area you have, the more chance you have of gaining purchase onto the asphalt and actually putting that friction to good use. So that will affect your lateral force, but it's not actually affecting your coefficient of friction. The load applied to the tire, however, does change how much friction you're able to generate. The coefficient of the friction of the tire, you will notice some changes in that as you put more load onto it. Put simply, if you put more vertical load onto the surface with the same coefficient of friction, you'll be able to generate more frictional force. And so if you're able to load more weight onto that tire, it is in turn going to be able to generate more lateral force for you. This is not a linear function to infinity. There is a drop-off point where you get diminishing returns on this, especially considering that in order to put load on one tire, you're most likely taking load off of a different tire, which in turn is going to be lowering your overall friction by loading one tire and not the other. The other thing to keep in mind is the slip angle. Now, the slip angle is a bit of an odd subject to cover here. You can see that these lines this is our contact patch here. The lines traveled along this is showing the tread of the tire itself, which would normally just be longitudinal along the tire. But at this contact patch where the tread is in contact with the road, if you're turning this tire, it's going to be bending and distorting that rubber in a direction relative to the turn that you're making. How much this distorts is what's referred to as your slip angle. And the larger of a slip angle you generate, the more lateral force you're going to be generating as well. This is also different depending on how much vertical load you're placing on a tire, and you can see this on the graph demonstrated over here. As your slip angle increases, you are capable of generating more lateral force on the tire, different for each vertical load, up to a certain point, at which point the force is going to drop off. You'll see your lateral load drop, and then you'll eventually exceed the lateral load and the tire will begin to slip. Now, the tire slippage is going to bring us into our next topic, which is understeer. We'll look at understeer and oversteer independently, but we'll look at understeer first. Understeer is concerned with the amount of grip that your front tires are capable of generating at any given point. The general idea is that if you put your front tires in a situation where you exceed the maximum grip dictated by your friction ellipse, what's going to happen is the tire will begin to slip. That slipping is going to mean, at the front tire specifically, that slipping will mean that a steering input you give to it, so let's say you turn the wheels on a 45-degree angle, your car is not going to turn at a 45-degree angle if the tires are not static to the road. If you exceed the maximum amount of grip they're able to generate, the tires are simply going to be pushed across, and you're going to see a lower steering angle than what you're expecting. So the car will feel as though it's still traveling in almost a straight line, despite the fact that you're giving it more and more steering input. You can see on the little pictograph down here where you expect the car to go based on the steering input you're giving it. If the tires break free and start to slip, you're only going to be generating part of that lateral force that you expect, and your car is going to be pushed in a straighter line going off of the surface that you're hoping to stay on. The way to think what's happening is that you have your static friction and your kinetic friction. Now, hopefully at this point you're aware that the static friction is going to be higher than the kinetic friction. If you exceed your static friction limit, you enter the kinetic conditions at which point the tire is slipping across the ground. Now you're dealing with kinetic friction, which, as we know, is lower than the static friction is. At this point, your wheel starts to slip, and the total amount of force you're capable of generating has now dropped. In order to correct for this, you have to get below that static friction limit, below the kinetic friction limit, so that you can regain grip at the tires and then speed back up to enter your static friction again. So we can see this on the diagram down here. If this is on the red line, the amount of static friction you're capable of generating, this is in play when the wheel is still in good contact with the ground and the tire is not slipping. If you exceed this line, let's say on this orange point down here, where you try to generate a force larger than you're capable of doing at static friction, the tire is going to begin to slip. Now you're being restricted by kinetic friction instead. You have to lower the load being applied to those tires below the kinetic friction limit in order to regain that grip, at which point you can go back up to the static friction limit again. So if you exceed this, it's a game of exceeding it, dropping all the way down, and then slowly working your way back up. The way that you're going to correct understeer is, first, you want to decrease the steering wheel input. And so if you're trying to turn the car on a 30-degree angle and you start to slip, you want to lower the angle, let's say to 20 or 15 degrees, sort of turn back into where the car is already trying to go. This will apply a lower lateral load on the tire. If you straighten out your wheel and you're putting the car in more of a straight line, you're asking the tires to put less lateral acceleration on the car. Hence, you're lowering the load that they're undertaking and you're getting back within your limits of grip, which allows you to regain purchase of the road. Sorry about that. Back to there we go. You can also do this by decreasing the accelerator input. If you are pressing down the accelerator pedal and you're trying to accelerate the car forwards, you're placing that longitudinal load in the tires and you're lifting, you're pushing the car forward and you're asking the wheels to generate more force to maintain that turn. You're asking for a higher centripetal acceleration if you're trying to accelerate as you go through a corner. Hence, you're putting more load on the tires and you're exceeding that static friction again. So just back off of the pedal, lower the load in the tires once again, and get back within the kinetic friction limits. Finally, you can also apply the brakes gently. This will transfer more weight towards the front of the car. As you decelerate, weight will have a tendency to shift onto the front tires. Applying that extra vertical load might give you enough force to play with to get back within your friction limits. As we know, with your coefficient of friction, you apply the larger vertical load, you're capable of generating a higher friction force, and hence you can get back within the limits of grip again and have your tires loaded. So applying the brakes a bit can help. However, if you apply the brakes too hard and you lock up the tires, then you're going to be losing grip for sure. The tires will absolutely be slipping, and then you have no hope of regaining grip at that point. In practical application, we see understeer especially entering a corner too fast without enough load applied to the front tires, where as we see the car swing around here, the front wheels are turned all the way to the right. Despite this, the path it's following is still relatively straight and it is not capable of making it around the corner. This is the pitfall of understeer. The next situation we're going to look at is oversteer, and this is the same fundamental principles that apply to understeer, but happening at the back wheels instead. So this will happen when you apply too high of a load to the back wheel, you exceed that friction ellipse once again, and the back wheels lose grip. The same principles of static and kinetic friction are at play here, and also the same principles of you're trying to get the back tires to turn along, let's say, a 30-degree angle. You lose that traction, they're going to be trying to turn at a 15-degree angle. The difference is in how this is going to actually impact the car. When you lose traction at the front wheels, you're no longer going to be turning, and the car will just push towards a straight line. However, if you lose traction at the back wheels, but you still have traction at the front wheels will pull the car around at exactly the steering wheel angle you input, but the back wheels will try to almost pass the front wheels in a way where it will rotate the back of the car around, and in the end, put you on a tighter steering path than you originally intended, hence why it would be referred to as oversteer. If we look at this diagram here, it's the exact same principle where you exceed your static friction. You have to lower the load on that tire to get it back within your kinetic friction. That way you have grip on the tire again. Then you can work your way back up to static friction and get closer to the limit once again. If you want to correct for oversteer, it's the same idea of decreasing the load applied to the tire. The first way to do this is simply decrease your acceleration. If you have your foot to the floor and you're trying to accelerate, you're putting a large longitudinal load in that tire. It's very easy to exceed this limit, especially if you're in a powerful vehicle. And if the tires are continuing to spin and continuing to slip, you're not going to be able to get purchase on them again. So you need to back off and decrease the longitudinal load in the tire to get it back within its limits. And also, in terms of actual driving ability, in order to counteract the rotation of oversteer, you can do what's called counter steering, which is turn the steering wheel in the opposite direction in order to prevent the back of the car from swinging around. That way, even though you still don't have grip at the back wheels, you're able to keep your car in the same turning path that you desire and continue on your way through the corner. Counter steering is not going to help you get your back wheels back in their grip. It's not going to change the load on the rear tires at all. That's all due to accelerator input. What it will do, though, is keep you on the right steering path, and so it sort of mitigates the effects of countersteer. In practical application for oversteer, regardless of the corner entry speed, as long as the front wheels are in traction, if you apply too much input to the accelerator pedal and you lose traction at the back wheels, the back end of the car will just have a tendency to swing around towards the front, generally speaking causing a spin if not controlled properly. As a demonstration of countersteering, although understeer is mostly controlled just by slowing down, countersteering can control oversteer by turning opposite to the direction of the car's rotation. So here the car is trying to rotate around to the right, you steer to the left, and that keeps the front of the car pointed along the coordinating direction you wish to take and allows you to recover for the spin as long as the back end is not spinning too aggressively. And that covers the principles that we're going to try to look at today. We'll go a bit more in depth into some more weight transfer characteristics next, but please try to get a good understanding of understeer and oversteer. If there's any confusion, you can either contact me, send me an email, or go ahead. There's a lot of videos out there on this that will show you more practical applications, and you can get a much better understanding of it. Understeer and oversteer are the two most fundamental principles to how well your car is handling, and so it's crucial that you get a good understanding of these, what causes them, and also how we can mitigate them.